Let us go to problem 4.6. A majority circuit is a combinational circuit whose output is equal to 1 if the input variables have more ones than zeros. The output is 0 otherwise. Part A: design a 3-input majority circuit by finding the circuit's truth table Boolean equation and a logic diagram. Write and verify a Verilog. Okay, we'll skip part B. I won't be solving any Verilog based questions. Solution: let the inputs be x, y, and z. Output BF. The truth table is as follows: 0 0 0 has only no ones, so it is output is 0. 0 0 1 has a single one, so output is 0. 0 1 0 has a single one, so output is 0. 0 1 1 has two ones, so the output is 1. There are two ones and a single 0 in 0 1 1. That means the number of ones is greater than the number of zeros, so it is output is 1. 1 0 0 has a single one, so output is 0. 1 0 1 1 1 0 both have two ones, so the output is 1. 1 1 1 has all ones, so the output is 1. So F is summation of minterms 3 5 6 7. Let's simplify this using a K-map. We have three pairs, so the output equation Boolean expression is F is equal to xz plus yz plus xy. and the logic diagram would be xz yz plus xy. So that is the logic diagram. We need to add the three terms. So it is an OR gate. Alright, we'll skip part B. Problem 4.7. Design a combinational circuit that converts a 4-bit gray code given in table 1.6 to a bit 4 binary number. I guess they mean a 4-bit binary number. First part, implement the circuit with exclusive OR gates. Second part, using second part is again very long, we'll skip that. So table 1.6 would be the following: xyzw gives the gray code number and ABCD will give you the binary number. 0 in gray code is 0000 in binary. 0001 in gray code is 0001 in binary. 0011 in gray code is 0010 in binary. 0010 in gray code is 0011 in binary. Then 0110 in gray code is 0100 in binary. 0 triple 1 is 0 1 0 1. 0 1 0 1 is 0 1 1 0, and 0 1 0 0 is 0 triple 1. 1 1 0 0 is 1 triple 0. 1 1 0 1 is 1 0 0 1. 1 1 1 1 is 1 0 1 0. 1 1 1 0 is 1 0 1 1. 1 0 1 0 is 1 1 0 0. 1 0 1 1 is 1 1 0 1. 1 0 0 1 is 1 1 1 0, and 1 0 0 0 is 1 1 1 1. So if we write the min terms of the gray code, this is min term 0, this is 1 3 2 6 7 5 4 12 13 15 14 10 11 9 8. So we can write each of the binary bits as sum of min terms. A is sum of 8 9 10 11 12 13 14 15. B is sum of 4 5 6 7 8 9 10 11. C is sum of 2 3 4 5 8 9 14 15. D is sum of 1 2 4 7 8 11 13 14. And from that you can simplify and get A is nothing but x. Whenever x is 1, A is 1. Whenever x is 0, A is 0. B is nothing but x prime y plus xy prime, which is nothing but x or y. So if one among x or y is 1, then B is 1. C is x prime y prime z plus x prime y z prime plus xyz plus xy prime z prime. We can take out the x prime common and write it as y xor z plus x into y xor z prime. This can be further written as x xor y xor z, and D will turn out to be x xor y xor z xor w. So A is x, B is x xor y, which is A xor y. C is x xor y xor z, which is B xor z, and D is x xor y xor z xor w, which is C xor w. So the combinational circuit can be written as, you have x, which is A, x xor Y is B, C is B XOR Z, and D is C XOR W. So that is the combinational circuit for gray code 4-bit binary gray code to 4-bit gray code to 4-bit binary number conversion. Problem 4.8. Design a code converter that converts a decimal digit, that is 0 to 9, from first part the 8 4 minus 2 minus 1 code to BCD, second part the 8 4 minus 2 minus 1 code to gray. Solution: first we write the truth table for the conversion from 8 4 minus 2 minus 1 to BCD code. To take the input variables as W X Y Z for the 8 4 minus 2 minus 1 code, and the output variables are ABCD for the BCD code. 0 0 0 0 will be 0 0 0 0, 0 1 1 1 will be 0 0 0 1, 0 1 1 0 will be 0 0 1 0, 0 1 0 1 will be 0 0 1 1, 0 1 0 0 will be 0 1 0 0, 1 0 1 1 will be 0 1 0 1, 1 0 1 0 will be 0 1 1 0, 1 0 0 1 will be 0 1 1 1, 1 triple 0 will be 1 triple 0 itself, and 1 1 1 1 will be 1 0 0 1. That's the truth table for conversion from 8 4 minus 2 minus 1 code to BCD code for decimal digits 0 to 9. If you write decimal digit here, 0 1 2 3 4 5 6 7 8 9. Then using the truth table we can fill out K maps and simplify, and you will get A is Wx plus W y prime z prime, B is x prime z plus x prime y plus x y prime z prime, C is y XOR z, and D is z. I'll leave the logic diagram as homework. Then we go to part B. We have the decimal digit 0 to 9, and we have 84 minus 2 minus 1 code. The input variables are w, x, y, z. Then we have gray code, output variables a, b, c, and d. And we again write down the table. Now the output is not BCD, it is gray. So after 2, decimal digit 2 is represented in gray by 0011 and not 0010. And in gray the corresponding numbers will be and then you can simplify using K-maps to get A is wx plus wy prime z prime, which is the same as the A we had earlier. B is w plus xy prime z prime, different from before. C is xy prime plus xz prime plus x prime yz. D is y. The logic diagram is homework. Problem 4.9. An ABCD 2 7 segment decoder is a combinational circuit that converts a decimal digit in BCD to an appropriate code for the selection of segments in an indicator used to display the decimal digit in a familiar form. The seven outputs of the decoder A B C D E F G select the corresponding segments in the display as shown in the figure. Using a truth table and Karnaugh maps, design the BCD to 7 segment decoder using a minimum number of gates. The 6 invalid combinations should result in a blank display, and the figure is as follows. Segment A, B, C, D, E, F and G, and the numbers should be this is 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So whenever 0 is pressed, maybe say in a calculator, you should display 0 in the calculator screen, and for that you will have to light up the LED segments A, B, C, D, E, F and G must remain off. Then you will get a pattern as shown here. Similarly, when the number 1 is pressed, you want to display 1, so B and C should be on and all the other LEDs should be off. So the truth table will be as follows: decimal number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 10 to 15 are invalid because we only want to display a single digit, and all these numbers have two digits. The BCD code will be equal to the binary equivalent for the first 9 numbers. And for 10, 11, 12, 13, 14, and 15 in BCD, you will need two BCD numbers. So you will need 8 bits. First 4 bits will be representing the tens place, and the other 4 bits will be representing the units place. And they're invalid combinations. So what they mean to say here is, if the binary equivalent number is invalid, yeah, so if any other combination is given, then it's not a BCD code, so it's not a BCD input. And if it's not a BCD input, then your 7 segment display should not turn on any of the LEDs, so all of A, B, C up to G must be 0. And those combinations are 1010, 1011, 1100, 1101, 1110, and 1111. The 7 segment has 7 LEDs, which must all be 0 for invalid combinations. Next, for the number 0000, we want to display 0, which is this, and in that only the LED G is off and all others are on. So that should be our output combination. To display number 1, B and should be on, B and C should be on, all others must be off. To display 2, F and C should be off, the rest must be on. To display 3, F and E must be off, and all others must be on. To display 4, A, E and D must be off. To display 5, B and E must be off. To display 6, only B must be off. To display 7, F, G, E, D all must be off. To display 8, all of them must be on. To display 9, E must be off. Now we have a truth table for each of the output symbols A, B, C, D, E, F and G. So for each of them we can draw a K-map and simplify. If we write in terms of minterms, A is the summation of minterms 0, 2, 3, 5, 6, 7, 8, 9. B is summation of minterms 0, 1, 2, 3, 4, 7, 8, 9. C is the summation of minterms 0, 1, 3, 4, 5, 6, 7, 8, 9. D is the summation of minterms 0, 2, 3, 5, 6, 8, 9. E is the summation of 0, 2, 6, 8. F is the summation of 0, 4, 5, 6, 8, 9. G is the summation of 2, 3, 4, 5, 6, 8, 9. Then we simplify using K-maps to get A is W x prime y prime plus W prime xz plus W prime y plus x prime y prime z prime. B is W prime x prime plus W prime yz plus W prime y prime z prime plus x prime y prime. D is W x prime y prime plus W prime x prime y plus W prime x y prime z plus W prime y z prime plus x prime y prime z prime. E is x prime y prime z prime plus W prime y z prime plus W prime x prime z prime. F is W x prime y prime plus W prime x y prime plus W prime x z prime plus x prime y prime z prime. And G is W x prime y prime plus W prime x y prime plus W prime y z prime plus W prime x prime y. And the logic diagrams are homework for you guys. Problem 4.10. Design a 4-bit combinational circuit two's complementer. That is, the output generates the two's complement of the input binary number. Show that the circuit can be constructed with exclusive OR gates. Can you predict what the output functions are for a 5-bit 2's complementer? Let us write the truth table for the 4-bit 2's complementer. The binary number is represented by 4 variables A, B, C, D. The 2's complement is given by 4 output variables W, X, Y, Z. Binary number 0000. Its 2's complement is 0000. 2's complement of 0001 is 1111. 2's complement of 0010 is 1110. 2's complement of 0011 is 1101. 2's complement of 0100 is 1100. 2's complement of 0101 is 1011. 2's complement of 0110 is 1010. 2's complement of 0111 is 1001. 1000 is 1000 itself. 9 is 2's complement is 7. 2's complement of 10 is 6. 2's complement of 11 is 5. 2's complement of 12 is 4. 2's complement of 13 is 3. 2's complement of 14 is 2. 2's complement of 15 is 1. And from the truth table we can write W, X, Y, Z as the sum of minterms. W is the sum of minterms 1, 2, 3, 4, 5, 6, 7, 8. X is the sum of minterms 1, 2, 3, 4, 9, 10, 11, 12. Y is the sum of minterms 1, 2, 5, 6, 9, 10, 13, 14. Z is the sum of minterms 1, 3, 5, 7, 9, 11, 13, 15. Then you simplify using K-maps. We get W is A prime D plus A prime C plus A prime B plus A B prime C prime D prime. Take out the A prime common, A prime into B plus C plus D plus A into B prime C prime D prime. This is using De Morgan's laws. You can write this as A prime into B plus C plus D plus A into B plus C plus D whole prime, which can be written as A XOR B plus C plus D. X is B prime C plus B prime D plus B C prime D prime, which is B prime into C plus D plus B into C plus D whole prime. So it is B XOR C plus D. Y is CD prime plus C prime D, which is C XOR D. Z is simply D. We can predict that for 5-bit input, A B C D E, the 5-bit output VWXYZ will be nothing but V is A XOR B plus C plus D plus E. W is B XOR C plus D plus E. X is C XOR D plus E. Y is D XOR E. And Z is E. So following the same pattern as the 4-bit input 4-bit conversion, we can write for 5-bit conversion, but we still have to verify whether this is true or not, and that I'll leave as a homework to you. Write out the truth table for 5-bit binary numbers and the 2's complement of those 5-bit binary numbers. Find the simplified expression using K-map and check whether what we have predicted is actually correct or not. Problem 4.12, design. Where were we? 4.10. So we'll go to problem 4.11. Using 4 half adders, design a full subtractor circuit. I think they have made a mistake here. Design a 4-bit circuit. 4-bit incrementer circuit. and part B is design a 4-bit decrementer circuit. So an incrementer will add 1 to the number and the decrementer will subtract 1 from the number. So using 4 half adders in cascade, we can get the incrementer circuit. Each half adder will have 2 inputs and 2 outputs. One output is the carry output and the other is the sum output. Sum and carry and 2 inputs. So initially we add the 1 to the first we'll assume the 4-bit number is A3, A2, A1, A0. First we add 1 to the LSB A0, their sum is S0 and that carryover is fed as the input to the second half adder. To that we add A1, its output is S1 and so on for A2, A3, S3, S2, S1, S0 will give you the incremented number. Next we have to do a decrementer circuit. This is simple using a full ladder. If you have 4 full ladders, then it is very easy to get the subtraction a subtractor circuit that will subtract a 4-bit binary number from another 4-bit binary number. You can simply take the 2's complement of one of the numbers and add it to the original number, and you can do that by giving the initial carry as 1 and then complementing the each of the bits of the second number and feeding it as one of the inputs to each of the full ladders. Then the carry is cascaded similar to the previous question, but there is no direct way to do that using only half adders. So first let's write the truth table and see if we find some clues. Here is the binary number and the output of the decrementer. So 0 0 0 0, if you decrement by 1 it should be -1, but assuming it's a cyclic decrement, it will go to 1 1 1 1. That is, sorry, not a, it's not cyclic. What happens is if you subtract 0 0 0 0. If you subtract a 1 from this number, then you have to subtract 1 from 0. You can't do that. So what you do is, you say you borrow a 1 from somewhere, and this will be a 1, and you borrow the 1. So this will be 1 0 minus 1. 1 0 is 2, so 2 minus 1 is 1. 1 1 1 1 with a borrow of 1. So if you decrement 0 0 0 0 by 1, it will be 1 1 1 1 with a borrow 1. And since we are not concerned about the borrow, or in the previous case the carry out we had here, we didn't care about that. We'll write the decremented value as 1 1 1 1. Decrementing 1 from 0 0 0 1 will give you 0 0 0 0, and so on. Alright, now we have the truth table. We can simplify using K-map and find the expression for S3, S2, S1, S0, and it will so turn out that S3 is A3 prime, A2 prime, A1 prime, A0 prime plus A3, A2 plus A3, A1 plus A3, A0, which is nothing but A3 prime into A2 plus A1 plus A0 whole prime plus A3 into A2 plus A1 plus A0, which is A3 XOR A2 plus A1 plus A0 the whole prime, or A3 XOR A1 A2 plus A1 plus A0. S2 is similarly A2 prime A1 prime A0 prime plus A2 A1 plus A2 A0, which can be written as A2 prime into A1 plus A0 whole prime plus A2 into A1 plus A0, which is A2 XOR A1 plus A0 complemented. S1 is A1 prime A0 prime plus A1 A0, which is A1 XOR A0 complement. S0 is A0 prime, which is A0 XOR 1. Next we have the circuit to implement those functions. First half adder, we need S0. We get that by doing A0 XOR A1, A0 XOR 1, A0 XOR 1. If it is 0, there is no carry. If A0 is 0, if A0 is 1, so This half adder, carry of a half adder is the AND of the two inputs to the half adder. The sum is the XOR of the inputs to the half adder. So the carry of this first half adder will simply be A0 and 1, which is simply A0. That's what's going out. Now you can feed that as the input of the next half adder, and S1 is A1 XOR A0 complement. So you can give A1 XOR A0, pass it through a NOT gate, will get. So the half adder will give you A1 XOR A0. S1 is the complement of that. And the carry of this half adder, we won't use that. It is A1 A0. In none of our expressions do we have A1 A0 used directly, so we'll leave it as it is. Now for the third half adder, we'll do the OR of, we'll use an OR gate to get OR of A1 and A0 and pass it as one of the inputs, and the other input will be A2. So I'll get A2 XOR A1 or A0. You complement that, you will get S2. Similarly, you take the OR of A1 and A0 and OR it again with A2. You will get A1 A2 or A1 or A0, and that will be XORed with A3. That will give you A3 XOR A2 plus A1 plus A0, and the complement of that will give you S3. So you will need 2 OR gates and 3 NOT gates along with your 4 half adders to get the proper circuit. Alright, that's it for session number 6. I'll meet you in session 7.